in this section and for the rest of this chapter, we want to study the second part of the headline of chapter 2, namely so-called series. Series are somehow infinite sums, so to say. I will say more on this in a moment. And they're basically looking quite strange in the beginning, but you should always keep in mind they are special examples of sequences, as you will see. And we will study this type of sequence, which has a kind of complicated behavior sometimes, but this is kind of a special case of sequences which occurs often quite naturally. The second part of that then here says convergence tests. The point is that to show the convergence of a series by the methods we've seen so far is actually quite difficult, really complicated. There are some cases, but there are so-called convergence tests, namely some criteria on a series, on such an infinite sum, that are checked quite easily, or not easily, but they are kind of, you have explicit conditions from which you can derive convergence of a series, as we will see. So these convergence tests, as we will see in the later part of this section. Okay, so I'll motivate a very, very naive example, or very simple example. So let's assume we have some container, and we have, so some, I don't know, a big plastic box or whatever, and we have some liquid which is running into this container. So let's say some liquid is running into a container through some pipe. Okay, we assume that this liquid is running in there, but if it's kind of running all the time, at some point the container would be overflowing. But what happens if the stream of this liquid becomes thinner and thinner? So there's less and less liquid running in. Is the container at some times big enough, or will it just flow over? So at some point this thing there might be so few liquid running in there after a reasonable amount of time so that everything stays in the container and the container turns out to be big enough. So to formalize this, let's say we have AN should be the amount of liquid running into the container in the nth minute, so in minute n. Okay. If we now look at the liquid that is contained in this, that's in this container already, this means that after n minutes, so the total amount of liquid in container after n minutes. This is now a very simple expression. It is the liquid running in the first minute plus the liquid running in the second minute and so on until the sum, the liquid running in nth minute. So this is the total amount that's then in this container. So if we now want to know if our container is big enough to contain the whole stream so that all the liquid can fit inside, we have to ask what happens if this n becomes bigger and bigger. And this sum here can now be seen as a sequence in its own right. So if we, let's say we call this Sn, S like sum. So we could consider the sequence Sn and check if this sequence Sn would converge. If it converged and if its limit was kind of smaller than or equal to the volume of the container, we would be relieved because nothing would flow over, but as soon as we would get bigger, or if this would not converge, if this would really become bigger and bigger and infinitely big and diverge to infinity, then of course the container at some time would be overflown. Right? So this is a very, very simple example. So the question is here now, will the container flow over or not? Okay, and this is kind of the way that infinite sums in some sense pop up. So we take a sequence of such sums which become bigger and bigger and bigger, which we can kind of somehow consider as an infinite sum, although I really don't like this term because it's quite informal. So, but we need to formalize this. So we need to formalize the notion of an infinite sum. Okay, and to give you motivation, just to give you, forget about physics, let's do math. Just write down some numbers. Assume we take the following sum. We just take 1, then we add 1 over 2, then we add 1 over 3, and so on. 1 over 4, 1 over 5. What does this infinite sum give? Will this kind of be bounded by some bigger value? So will this be really a finite value, or will this become infinitely big? The same thing we can do for like a similar sequence, but this time we don't take all these fractions, but we just take the denominators which are powers of 2, which means we take 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus and so on. And we can ask again, does this somehow stay beyond a finite value, and can we interpret the sum as a finite value? So can we consider kind of a fixed number of such, the sequence of finite sums that we get here, and see what happens if we go to infinity. And as we will see soon, this thing here indeed is a finite value, so we can give this infinite sum a finite value, while this doesn't. This goes to infinity. We shall see this a few blackboards down from here. Okay, so these are, again, we want again formalized by sequences of sums. And these sequences of sums is what we call the series. Now we are getting serious. Sorry. Okay, definition 263. So again, as we did before, we work in the real numbers or the complex numbers. So in general, you can take the complex numbers, but if you prefer to ignore the imaginary units, work in the reals. And we let an be a sequence in K. Then the sequence Sn, where Sn is simply the sum of the first n elements of the sequence. So the sum from k equal to 1 to n, a k for all n in n. So this sequence is called the series of an. Okay, this is the object of study, and we usually denote this in a different way. Namely, we denote this really as an infinite sum by sum n from 1 to infinity an. And so far, this is just notation. So, infinite sums, we haven't dealt with them before, but this is kind of just how we denote this series. Okay, a bit more terminology. Sn is then called the nth partial sum of the series. So we only sum part of the series. Nth partial sum of the series. There's a slope in my, sorry. Just need to, okay. Should write down more carefully. Okay, then the series sum from n equal to 1 to infinity of an is called convergent or divergent, and our definition, you can guess what I mean. If this sequence of the partial sums is convergent or divergent. So if the sequence Sn, which is basically by definition this series, is convergent divergent, just to make this clear, so I will write this simply that this expression, this infinite sum, converges when I actually refer to this sequence. Okay, and if the series converges, then we abuse notation. Namely, we also then denote the limit of this as the sum from n equal to 1 to infinity as well. So this then denotes the limit n to infinity as n, so really an element of k. We also denote this then as this infinite sum. This turns out just to be quite, of course it's a bit imprecise, since this, on the one hand, we refer to the sequence, on the other hand to its limit, but it turns out that this notation is actually quite useful and quite intuitive when you're getting used to it. Okay, and of course, as for sequences, if k is R, we call it a real series, and if k is equal to C, we call it a complex series. Okay, so now we've got this notion of infinite summation by simply using, again, sequences. So sequences of finite sums which sum just more and more elements. Okay, I will introduce some additional notation after erasing the board. As it turns out, one also has to study, or one often studies series which have different starting values other than 1. So far we have seen the sum from n equal to 1 to infinity, but we could have some sum going from n equal to some number like 5, 10, whatever, then going to infinity. And we want to study the convergence of these ones as well. So this is basically just formalism, but I will just introduce this quickly in the definition to have this once on the board. Precisely. So assume we have some given starting value, which I call n0, which should be just an integer. And assume we have complex numbers, an, so this could also be fine for real numbers as well, which is of course contained in the complex numbers. But this time we don't have numbers for n and n, but for all n and n, n and z, which are bigger than n0. So bigger than or equal to n0. These are complex numbers. So in this case, we just define the sum going from n equal to n0 to infinity an. This is, again, a series in the sense we had before, so as a series starting with 1, namely as the following series. We just take the index n equal to 1 to infinity, and then sum over a, and then just modify the index, n plus n0 minus 1. Okay, this is a series, since we start really with the index 1. And if you just take a look what happens, if we insert 1, we have 1 minus 1 here, so we start with a and 0. This is the first term of the series, the first element here. The second one would be then, we had n equal to 2, then this would give a and 0 plus 1, so the next one, and so on and so on and so on. So we can just shift the index, modify the index, play around with it, so we get really a proper series starting at 1. So this is how we can handle basically all series starting with any given value. And I will occasionally refer to these things as series as well. But only if it's clear what it's meant. So here, the nth partial sum, just to have this there precisely, this means that the nth partial sum of this thing here is so the nth partial sum of this guy. So this would be Sn, and by definition just of this series here, this would be the sum of k equal to 1 to n of a and 0 plus k minus 1. And if we just shift the indices back, since it's a finite sum, there's no problem if we just modify the indices. This means we go from k equal to n0 up to n plus n0 minus 1, a k. Okay, so we just consider this n0 element as the first one, and then take it from there, and then do it the same way as if it was a sequence starting from 1. Basically, we just relabel the indices. Okay, and the same way we say that this expression, sum from n0 to infinity an, is convergent or divergent if this corresponding series is convergent or divergent. So the series n from 1 to infinity, a n plus n0 minus 1, if this is convergent or divergent. Okay, so much for terminology and notation. So now it's time for some examples. So some of you might now think, okay, just intuitively, how can an infinite sum be a finite value? Or how can we then prove that some infinite sum is a finite value? This looks strange. And I will now give you 2 examples. It's often quite hard to compute really the explicit value of a series, so the limit of its partial sums. But I will give you 2 elementary examples where we can really do so. The first example is the series from starting with 0 to infinity. So this is then here the case of n0 equal to 0 of q to the power of n, where q is just a complex number. Okay, this series has a name. This is called the geometric series in Q. Okay, so we just take the powers of some element, so where n becomes bigger and bigger and bigger. So, yeah, we have to So we want to compute and want to show when this converges and when it doesn't, or at least investigate if we can say something about when, for which kind of Q it converges and for which it doesn't. So we consider the partial sums. So that Sn, this would then be the sum k from 0 to n of q to the k, be its nth partial sum. And if you now think, this sum looks familiar, then that's a good sign, because then you did the exercises. This sum was contained in the exercises, and because I had you prove something about this, namely by exercise 2b from sheet 2, there you have proven that this sum, so Sn, is equal to the following: 1 minus q to the n plus 1 divided by 1 minus q, as long as for q in C without 1. So q equal to 1, of course, has to be excluded, otherwise this expression isn't well defined. So we have this funny quotient here, and if we take a look at this, so what the value of this sequence would then be, of the series would then be the limit of the partial sums, so the limit of this expression. But for this expression we can use the standard limit rules, and this sequence q to the n, or q to the n plus 1 is a subsequence. This is what we've already studied in section 2.1. Yeah, that we've seen that this here converges to 0 in case that the absolute value of this q is smaller than 1. So this shows if the absolute value of q is smaller than 1, then by, it was theorem, I've written it down somewhere, 2.6. So this infinite sum, n from 0 to infinity q to the n, this would then be, just by definition, the limit of this expression 1 minus q to the n plus 1 over 1 minus q. And by our standard limit rules, this is 1 minus the limit n to infinity q to the n plus 1 divided by 1 minus q. And this theorem that I quoted shows that this goes to 0, which means that this is precisely 1 over 1 minus q. So this is really the limit of the sequence. So this infinite sum takes this value. Isn't that nice? I find this kind of a beautiful series. Okay, and now we can also answer one of the questions that I had on the blackboard as a motivation in the beginning. Namely, I just want to compute this stuff for particular values of q. Namely, the first situation would be q equal to 1/2. Namely, then we would get this infinite sum that I had in the beginning. We had 1 plus 1/2 plus 1/4 plus 1 over 8 plus 1 over 16 and so on. So all powers of 2. As a series, this is the same as the sum for n from 0 to infinity of 1/2 to the power of n. Right? This is simply 1 divided by 2 to the n, and this gives precisely this sum. But by this formula here, the absolute value of 1/2 is, of course, smaller than 1, which means that this is 1 divided by 1 minus 1 over 2. So this is 1 divided by 1 over 2, which just gives 2. So the whole sum of these powers of quotients here, 1 over the powers of q, of 2, simply gives 2 in the end. Right? That's a nice little formula. There's even a stupid math joke about this. Let me say if I get this correct. An infinite number of mathematicians goes into a bar. The barkeeper asks them, what can I get for you? The first one orders 1 pint of beer. The second one orders a half pint of beer. The third one orders a quarter pint of beer. The fourth one orders an eighth pint of beer, and so on. And at some point, the barkeeper just pours two pints of beer, puts this in front of them, and says, you guys should really know your limits. Yeah, anyway. Okay, so this is this infinite sum here. Another thing that you could do would be to include minus 1/2 here instead of 1/2. Then we would get the following infinite sum. We would have 1 minus 1 over 2 plus 1 over 4 minus 1 over 8 plus 1 over 16 and so on with alternating sign. This would be the same as the sum n equal to 0 to infinity minus 1/2 to the power of n. So this is by this formula here, it's the same as 1 divided by 1 plus 1/2. This is, of course, 3 over 2, so in the end we get 2. No, wait, I did some. Yes, no, right. 2/3. Okay. Now, why did I use this blackboard? I was so enthusiastic that I used both blackboards, so it's halfway invisible. Sorry about that. Got carried away. So this is really, the behavior of this geometric series, and really you can compute some other sums here, of course, if you just add, put in some other nice little numbers here that you're interested in. And so you get a lot of examples by this. So this is how you can really compute infinite sums whose total value turns out to be finite in the end. And now there's another example. Oh, sorry, I forgot one case that maybe I can squeeze this in here. This was in the case that the absolute value of q is smaller than 1. And in the case that the absolute value of q is bigger than 1. Then we've seen that this sequence, which appears here, in, which is part of this sequence whose limit we're taking, this is unbounded, which shows that this whole fraction is unbounded. So this is by example 2.11. There I've shown that then the sequence is unbounded. Which means that the sequence of partial sums is unbounded. And so if it's unbounded, it cannot be convergent by a theorem from before. So hence, in this case, the geometric series really diverges. So in this case, we can't. Okay, the case of q equal to 1, we will see some examples of this later, but then it's also not that easy to handle, but yeah, we'll see. Okay. Yes. Okay, another example. Now, this was still quite abstract since we still had some room, we still had some q to insert there. Now we really get something which you can really write down as a sum of numbers. So very honest to God series of numbers. Namely, we take the series 1 divided by n times n plus 1. Okay, so this would be, if we start computing this, so if n equal to 1, we would get 1 over 1 times 2, so it's 1/2. If we take n equal to 2, we get 2 times 3, which is 1 over 6. Okay, then we get 1 times 3 over 4. 3 times 4, which is 12. Then we get 4 times 5, which is 20. Then we get 5 times 6, which is 30, and so on and so on. So we can really do such an infinite sum of fractions that become smaller and smaller. And we will see that this converges, and that we can compute this value as well. Namely, for each n in n, we can do a little trick with this sequence that we are summing up here. For each n in n, we get the following: 1 over n times n plus 1. This is the same as n plus 1 minus n in the numerator. So we just add and subtract n, divided by n times n plus 1. And now we can see that we can kind of decompose this as a difference of two fractions, simply by n plus 1 over this minus n over this. And in both cases, we can reduce the fractions. So in the first case, we get 1 over n, and in the second fraction, we get 1 over n plus 1. Okay, this means for the partial sums, I mean, this is the sequence of partial sums is the one whose limit we have to compute. So we have to determine the sequence that we have to study. So for the partial sums, we get that Sn, which is by definition the sum from k equal to n, 1 over k times k plus 1. And this is then, by this computation, the sum from k equal to 1 to the n, 1 over k minus 1 over k plus 1. And this is an example of what we mathematicians call a telescopic sum. Namely, let us write down the elements here in this explicit way of writing down. So we start with k equal to 1, then we get 1 minus 1 over 2. Okay, the second summand would then be k equal to 2, then we would get 1 over 2 minus 1 over 3. The third summand is 1 over 3 minus 1 over 4, and so on. until the end, we get 1 over k minus 1 over k plus 1. Okay, so if we take a closer look, and there's no coincidence, we see that many things cancel each other out, because always the last one of the one summand is the first one of the next summand. So always these cancel each other, these cancel each other, these cancel each other, and so on and so on and so on. So what remains? The only things that remain is this one in the end, in the beginning, and the very last one, since this doesn't have a companion from the other summand, which so that they cancel out. So this means everything that remains is 1 minus 1 over k plus 1, which is actually surprisingly, n, not k. K was the index of the sum. So 1 over n plus 1. So this means the value of the series from n equal to n equal to 1 to infinity over 1 over n times n plus 1. This is the same as limit n to infinity as n, which is, by this computation, the limit of n to infinity of 1 minus 1 over n plus 1. We know that this goes to 0. This is, of course, constant, so this becomes 1. And so this whole sum converges to 1. This infinite sum here gives a 1. Okay, these are two nice explicit examples. And now we want to kind of focus on the case, so what can we say about convergence here? We will see some more examples later on, but for now we want to see kind of how can we, I mean, of course this, that we could compute these two series was because the partial sums had a very simple way of describing this. This was simply by realizing that the partial sums have this telescopic style, so we get a very simple thing in the end. And here we had a simple expression which you had to prove by induction, which was some expression which didn't involve sums, and so this is why we could compute these values of these sequences. In general, this is not that easy. So in general, there are many series where we can show convergence but not compute their values, or not without great pain, or without using heavy machinery. And I will give some example of this later. Okay, so now we want to first study the convergence of series in a better way. So how can we see convergence if we don't have these beautiful formulas for partial fractions? Okay, the first observation, this is something really simple, it almost doesn't deserve to be a theorem. Take a real sequence, so this time only for real sequences, and assume that an is non-negative. For example, this series we had before is a perfect example of this. For all n in n, then the following holds. The series of an is convergent if and only if the series is bounded. And not only bounded, bounded from above. Obviously, this is bounded from below, always, because everything is non-negative, so all the sums are non-negative, so it's bounded from below by 0. Okay, why is this the case? Oh, yeah, right. And otherwise, so if it's not bounded from above, the sum diverges to plus infinity. Okay, so why is this the case? Proof is very short, so I will do this on this blackboard here. Okay, this direction is clear. This is simply because every convergence sequence is bounded. So this is simply a special case of theorem 210, which said precisely this. So every convergence sequence is bounded. The interesting part is the other way. But here it's very simple. Since all terms of the sequence are non-negative, so an bigger than or equal to 0 for all n in n, we can see that the sequence of partial sums, which would then be the sequence of sums from k equal to 1 to n of a k, n in n. So we see with n becoming bigger, we just add more terms which are non-negative, and this means that this sequence here is monotonically increasing. And then, since if we assume now that's bounded from above, then we get from our theorem about convergence of monotone sequences, that was theorem 235. that the series converges. And in the other case, so if it's not bounded from above, we have something which is monotonically increasing and unbounded. Not bounded from above, so it has to go to plus infinity. So this means this follows directly. I won't write this down again, but this follows immediately from this monotonicity and from not having an upper bound. Okay, so this is the first observation. So to show that this series converges, even if we can't compute this limit, we just need to find an upper bound for this expression, and this is sometimes much easier. Okay, I will give you now another classic example of a sequence, but I will have to erase first. We'll study another important example, and that's the other sum I had on the blackboard in the introduction before, namely the following. So that's example 267. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. So this, which as a series reads like this, sum from n equal to 1 to infinity 1 over n. And this series has also a name, and this is very important series. It's the so-called harmonic series. Okay, so here also the fractions become smaller and smaller and smaller. Here we will see that this actually does not converge to some finite value, but that this sum becomes infinitely big. So to show this, this is like in this theorem before, we had said something about convergence of series of non-negative real sequences, which is precisely the case here. 1 over n is always non-negative. So this is convergent if and only if it's bounded. So the question if it's bounded or not, and we will now show explicitly that the sequence of partial sums is unbounded, which then shows that it's divergent. Okay, so for this case we study the partial sums, so that Sn be the sequence of partial sums. And we consider a special case, namely for each k in n. And what I now want to do is to study a subsequence of this sequence of partial sums, which is unbounded, which is of course enough to make the whole thing unbounded. So, namely I want to study the ones where n is equal to a power of 2. I study the sequence S2 to the power of k and consider these partial sums. So to write them down, we got the sum from n equal to 1 to 2 to the power of k, 1 over n. Okay, this is now a finite sum that we can reorder a bit, namely 1 plus 1/2. The first sums we write explicitly, and then the next ones can be kind of written down by just reordering or reassembling the summands. This is something you cannot do for an infinite series in general, but you can do for these finite sums. Namely, we can do the following summation. We sum over all I from 1 to the k, and then inside we take the following sum. We go from n equal to 2 to the I plus 1 to 2 to the I plus 1. So here I plus 1 is in the exponent. Over this and take 1 over n. So using this sum of these different sums, so we first take these sums and then sum them up, and of course since this is a field, it's associative, so this order doesn't matter. This means if we write this down explicitly to make this maybe a bit more visible, so we have 1 plus 1 over 2, then the first of these sums would be I equal to 1, which means we would have n equal to 3, and here we would have n equal to 4. So the first of these things in the parentheses is 1/3 plus 1/4. Then, for I equal to 2, we would start with 5, so 1 over 5. And here we would have 2 to the power of 3, which is 8. So this means we take 1/5 plus 1/6 plus 1/7 plus 1/8. And now you get the idea. The next thing would be, I don't write them all, 1/9 plus ... plus 1 over 16, so to the next power of 2. Plus ... and the last one is 1 over 2 to the k plus 1 plus plus 1 over 2 to the k plus 1. Okay, that's a nice way of making simple things complicated, but it turns out that this has a useful property. Namely, if we take the following, if we take the things inside the parentheses and look at them closely, we get a nice estimate. Namely, for each I between 1 and k minus 1, so for each wait. Sorry. Yeah, sorry, this is k minus 1 here. I'm sorry, and here also. The last one is 2 to the power of k, of course, in the 2kth partial sum, and here it's 2 to the k minus 1. Oh, still, you can still read this from the camera. So for each I, we want to estimate the sum in the parentheses. So we take a look. N goes from 2 to the I plus 1 until 2 to the I plus 1. Okay, and of course, with n becoming bigger, this whole thing is getting, the fraction here is getting smaller. So we can estimate this from below if we just estimate every summand by the last sum in the fraction, so by the biggest value of n, which is 2 to the I plus 1. This means this is bigger than or equal to the sum n equal to 2i plus 1 to 2 to the I plus 1, 1 over 2 to the I plus 1. Okay, this is now constant. This is not dependent on n anymore. So this is just a multiple of this fraction here, and the multiple is now the number of summands here. And if we take a look at this, 2 to the I plus 1, and here we have 2 to the I plus 1, then if we just think, let me squeeze this in the corner here, 2 to the I plus 1 is the same as 2 times 2 to the power of I, and this is then the same as 2 to the I plus 2 to the I. So we go from 2 to the I plus 1 to 2 to the I plus 2 to the I, which means these are 2 to the I summands. Okay, and this, of course, gives 1/2. So each of these parentheses here is at least 1/2, which means if we estimate our S2k, this is the same, this is bounded from below by 1 plus 1/2 plus the sum of I equal to 1 to k minus 1, and then this is estimated from below by 1/2, so we can estimate this here. And now we see again that this doesn't depend on I, so it's again just k minus 1 copies of 1/2. Here we have one more copy of 1/2, so this is simply 1 plus k over 2. So, yeah, to make this, maybe let's write this down here explicitly. So we have shown that this partial sum s to the 2k is bigger than or equal to 1 plus k over 2 for all k in n. And now we see this diverges to plus infinity, obviously, because k is just exploding and then the whole thing is exploding, which means that by this estimate, and by an estimate we had before, that this partial sum also is going to infinity. So this means by theorem 242, so if something is bounded from below, the chair again, sorry. If something is bounded from below by a sequence which diverges to infinity, then the sequence has to go to plus infinity as well. So this means that S2 to the power of 2k, k in n, diverges to infinity, to plus infinity. And this particularly means that the sequence of partial sums cannot be bounded. So this is unbounded. And by the previous theorem, this already implies that the series cannot converge. So this is not convergent, since it's monotonously increasing. This was then theorem 266. It follows that this sum is, 1 over n, not Sn. This is divergent. And not only that, it goes to plus infinity. And this we can also denote as the sum of 1 over n is plus infinity. So this is an example of a divergent series. So here we really don't have this phenomenon that kind of this, we stay below a threshold and the infinite sum adds up to some finite value. Here this really becomes big. And this is kind of one of the most useful examples, as we will see later on. Okay. Now, what do we know about convergence of sequences? So now we just have seen the simple case where we had some real sequence of non-negative real numbers, and then we know, okay, we need an upper bound. Okay, but this upper bound is also not falling from the sky. So what can we tell? What can we tell in general about convergence? And there is a nice necessary criterion. Namely, let's say an sequence is a sequence in R or in C, doesn't matter again. If the series over this, of this sequence converges, then the series must have a nice property. Namely, then it must follow that the whole sequence, an, converges to 0. Which somehow makes sense. If we sum infinitely many things up, to even have a chance of getting something finite, these elements have to become very, very, very small, so very, very close to 0. So to show this, it's also not that hard to see. So let Sn be the nth partial sum. So we assume that this converges. Since now we take the following subsequence, we take Sn plus 1, n in n. Since this is a subsequence of Sn, we have by assumption we know that Sn converges. So this as a subsequence converges against the same limit. It converges. And not only that, the limits are the same. So what we get is that, to write this in a more complicated way, 0 is the difference of the two limits, namely limit n to infinity Sn plus 1 minus the limit n to infinity of Sn. Okay, by our rules for convergent sequences, since we know that these here are convergent, this is the same as the limit of Sn plus 1 minus Sn. But if we take a close look at what's going on here, this is just the limit of the sum from k equal to 1 to n plus 1 ak minus the sum from k to 1 to n ak. So this means we just subtract almost every summand, and the only thing that remains is an plus 1. So we've seen that an plus 1 converges to 0. But since this is a subsequence where only the first one is missing, for convergence purposes, the first one doesn't matter. So this means that the sequence itself, if we consider an, this also converges to 0. And this is what we wanted to show. So this is a nice criterion. So at least something, if we see that the series itself does not converge to 0, we don't even have to ask for convergence of the series, because this can't happen. But the bad news is, it's not enough. Namely, just to give a simple example, I formulate this as a remark. Remark 269. The converse of this theorem is false. So if we know that this limit is 0, it does not already imply, it doesn't follow that this converges. And the example is right here on top. Here, for this harmonic series, we know that the sequence 1 over n clearly goes to 0, but the whole sum goes to infinity. So this would be a counterexample for the other implication here. So this is a necessary thing. It is necessary that this holds, but it's not sufficient. So it does not show, it does not imply convergence here. It's only a necessary statement. So we can only use this to say, okay, there's a sequence which does not converge to 0, so we don't have to discuss the series. It can't converge. And this way we can use this. So this is false. And the harmonic series here is a counterexample. Okay, so this is, this is the counterexample here. So this is, again, not, this is interesting, but of course this doesn't help us with finding convergence of sequence. It's just a very basic criterion, so very rough. Okay, if this doesn't even go to 0, then we don't have to discuss things yet. But as the next thing, we want to discuss these so-called convergence tests that are already announced in the headline of this section. So there are really some criteria where we can say if this and this holds, then the series converges. And we start considering the first one, the simplest one maybe of this, and then we will go on from there and establish several ones.